So let me start now. The Monte Carlo method is of broad applicability, and it's fairly easy to use, and it's robust. And it can often be fun. So I'll try to communicate some of that today. What you must know is that computers can generate huge numbers of pseudo-random numbers. One can then use these random numbers to create zillions of random virtual events that fall into a selected class. And then one can use these events to compute the properties of the selected class or to define ideal members of that class. And so the two things in the Monte Carlo method are randomness and selection. So here's a common application of the Monte Carlo method, and it's simply to approximate the integral of a function over a region R and inside a box of volume V. And what one does is one has the computer generate n random values of the n vector x, and one then basically takes the average and only counts those x's that lie within the region R. And besides randomness, you see, it's the selection of only those x's that are inside the specific region. Let me give you an example of this. Suppose you want to integrate the function f of xy. This is, of course, a trivial example, an exponential over a square root. It could be arbitrarily complicated, and it really, whereas if you're doing things with your fingers and your mind, then the complexity of f is a big deal. But if you're using the Monte Carlo method, the computer really doesn't care much how complicated f is. Of course, the computer doesn't care about anything, it's just not conscious as far as we know. But in any event, let's suppose you wanted to integrate this function over the quarter of the quarter of the unit disk in which x and y are both positive. The volume here, V, is pi over 4, obviously. Here's a Fortran 90 program to integrate the function. Fortran, I find to be very convenient. It's a language that was invented 50 years ago for numerical calculations. It's not designed for video. It's not designed for prose. It's only for numerical methods and calculations. That means that it's simpler to use. It's simpler to read than many other programming languages. Because it is so simple a language, compilers can optimize Fortran code to a higher degree than they can optimize other codes that are more sophisticated and in which the codes that allow the programmer to invent all kinds of clever abbreviations and deficiencies. Anyway, the compilers are available from an organization that supports both Fortran and C, and it's called G-Fortran and GCC. Those are the programs that do the integrations, or that compile programs written in Fortran or C. I think I'm going to skip this program because some of you know Fortran and will think this trivial. Others will think Fortran is something you don't want to learn because it's 50 years old. In any event, you can read this if you want. I've distributed the slides along with the announcement, the reminder of my talk. In this particular example, well, maybe I will say something about the Fortran. What you do here is you say call random seed. That selects a new seed. So you have a new sequence of random numbers. And then you say call random number, RDN, and now you have a random number. In fact, up here, I defined random numbers as RDN as being 2 random numbers. And so we have, so this operation here, call random number RDN gives us RDN1 and RDN2. And then I use them to do the rest of the integration. F of XY, you see, can be defined up here simply in essentially just an ordinary mathematical way. The D here just means double precision. So these are ordinary random numbers. These are called pseudo-random numbers. There are better random numbers called quasi-random numbers. And the University of, I think it's this Florida State University maintains a repository on Fortran C and their applications to Monte Carlo integration. And at that organization has programs that do these particular integrations. In fact, I can show you their URL. It's this thing down here. Anyway, if you just go to Florida State University and look for Burkhardt, you can find it. So the advantage of the quasi-random numbers is that the error falls as 1 over n to the 2/3, or even 1 over n, which is faster than, I'm sorry, that should be a square root of n that one gets with pseudo-random numbers. So that's a typo there. That should be square root of n. So numerical integration is one example of a sort of a very simple example of the use of Monte Carlo methods. A more sophisticated use is simulation of what one expects in an experiment, a physics experiment, or for that matter, a more general experiment. And one example is, suppose you're a graduate student working on an experiment that measures muons produced in a detector underground somewhere, and or maybe on the surface. Anyway, the probability P that a cosmic ray will make a muon in the detector is very small, but the number n of primary cosmic rays is very large. And so Pn might be, in this experiment, we might think it would be 0.1 muons per day. And since n is huge and P tiny, this probability distribution is Poisson. And so the probability of n muons on any particular day is given by this. In the absence of some problems with the experiment, a failure of the anti-coincidence shield, or some problem with the other problem with the detector, or some astrophysical event that you should be paying attention to, like a supernova in a nearby galaxy. And one way to analyze to know whether your detector is behaving sensibly or whether something crazy has happened in the universe, or some failure has occurred in your apparatus, what you can do is produce, for example, 1 million 100-day histories of detections of muons distributed this way. And that would tell you whether the data you're getting are reasonable or not. Here's a Fortran program that does that. I'm certainly not going to take you through that because it's more complicated even. By the way in which you would run this program is you'd say gfortran muons.f90, and then you just say a.out, and that then produces the output. And I graphed the output this way. And so what you see here is this is the number of histories of 100 days in which a maximum of n muons is detected on a single day. Those are the boxes. And in 100 days, the curve. And so it's likely to get 1 muon per day. It's less likely to get, slightly less likely to get 2, considerably less likely to get 3 and 4, and then it falls off to something negligible. And in 100 days, you expect this kind of a distribution. That is to say, this, of course, is a log of the number of histories, log to base 10 of the number of histories. And this gives then a pretty thorough description, a description of the experiment, such that if something happens that's suspicious, you can say, well, does it look reasonable in view of these 1 million histories? And anyway, so this is just an example of the use of Monte Carlos in experimental physics. Of course, what actually takes place at the LHC and neutrino detectors is much more sophisticated. A different and important application in theoretical physics is to statistical mechanics. And as an example, let's consider the problem of protein folding, in which most of the progress, frankly, has been through artificial intelligence rather than actual Fortran or straight physics. But suppose we really were super physicists and knew the energy of any configuration x1 to x3n of the coordinates of the atoms of a protein. When I say of a protein, I don't mean a protein in vacuum. I mean a protein in the saline solution of the interior of a cell of some animal. So the question is, how would one generate a sequence of native states of the protein at a given temperature, T? And of course, the most interesting case for us is temperature of 37 degrees Celsius. And we'd be interested in proteins that occur or might occur in the human body. So what one would do would be to start with an initial configuration x0 and make random changes delta x in successive configurations x. X, remember, is a 3n vector. And let's say there are 1,000 amino acids, and each amino acid has, let us say, 100 atoms. Then that's 10 to the 5th coordinates. And So then you test whether to accept this change by comparing the energies E of x and E of x prime of the two configurations which differ by delta xi in coordinate xi. So in other words, you make a small change, one of the coordinates, one of the, what did I say, thousands of coordinates of the atoms of the protein. And these sequences of configuration should be ergodic so that you cover the whole space of the possible space of the protein. And it's important that the thing be symmetric. That is to say that the test to go from x to x prime when one is at x should equal the probability of choosing to test whether to go from x prime to x when one is x prime. So this is choosing to test. This is not the result of the test. And the key way of implementing this is something called the Metropolis Step. Roy Glauber once told me that this was invented actually by Fermi, and that during the Manhattan Project, Fermi described it to Metropolis and others who then eventually published it. So the Metropolis Step is to define x prime in terms of x and a suitable step size and a random number uniformly distributed between 0 and 1 in this way. So you say x prime is x plus, this is the size of the step, and this is a random number between 0 and 1. So half the time you increase xi, half the time you decrease xi. And the amount that you change it is by delta x. So there's a matter of judgment here as to how big to make delta x. And what you do, the basic rule of thumb is that you choose delta x so that you accept the change half the time. Now, how do you decide whether to accept or not? That's the Metropolis Step. If the energy of the new configuration is less than the energy of the current configuration, then you always accept the new configuration. If the energy of the new configuration is higher than the energy of the original configuration, you accept the new configuration conditionally with this probability, e to the minus e prime minus e over kt. And the way you do that is you generate a random number r between 0 and 1. You accept x, the new configuration, if the random number happens to be less than this. If the new configuration is rejected, the system remains in configuration x. A Fortran 90 description of this step looks like this. If new e less than or equal to old e, accept. And so you change xi this way. Otherwise, you call a random number. I see here, this should be less than or equal to this, then accept, and then you end the two if statements. So let me see if I can fix this. Yeah, let's see if, yeah, okay. Now, actually, let me actually fit that r dot le dot. This would be the Fortran 90 description. Okay, thermalization. So the next step is to vary the next coordinate, xi plus 1, and then you go through all 1,000 atoms of the protein. And that's called one sweep. Then after thousands or millions of such sweeps, you say the protein is thermalized. Once the protein is thermalized, you can start measuring its properties, such as its shape. And of course, the reason you want to know the shape is that the shape has a lot to do with the functionality of the protein. And so if you're trying to advance medicine, you want to know what the shape is of the protein. One then computes a physical quantity every 100 or 1,000 sweeps and takes the average of these measurements. That average is an estimate of the mean value of the physical quantity at a given temperature. So why does this work? And let me just say that what I have been implying, but should have stated at the beginning, is that the goal here is to find a sequence of configurations of the protein that the protein would assume at temperature T in its environment inside a cell. And so the E has to reflect not only the properties of all the atoms, but the properties of how the atoms would be when surrounded by water molecules, sodium ions, magnesium ions, and so forth. So it's so in fact, the reason why AI has been the key to solving the protein folding problem is that as physicists, we haven't been smart enough to figure what E of X is. But suppose we did know what E of X was, or suppose we were considering a different problem where we did know what E of X was. And what we wanted then was a sequence of configurations of the protein distributed according to the Boltzmann distribution, e to the minus the energy over KT. And so consider two configurations, X and X prime, that respectively have energies E of X and E of X prime. They're occupied with probabilities P sub T of X and P sub T of X prime as the system is thermalizing. And what we want is to get a sequence where P of X is the Boltzmann distribution, which is to say like this. And so if the energy of the new configuration is less, then the Metropolis step says that we're going to accept it for sure. And so the rate of going from X to X prime is the rate V of choosing to test X prime when one is at X times the probability of being at X, because one always accepts. So it's just V times PT of X. On the other hand, the reverse rate of going from X prime to X is the same expression, V PT of X prime, but we accept that new configuration conditionally only with probability e to the minus delta E over KT. So the net rate of flow from X to X prime minus X prime to X is the difference of these two. That stops when this thing is zero. The thing inside the parentheses is zero, but that's when P of T is equal to this. On the other hand, the thing with the X primes and the E primes is independent of X. So this thing is a constant times e to the minus KT. In other words, the X dependence of this is e to the minus KT, where E of X minus KT, since this other factor is independent of X. So the X dependence of this is that. In fact, maybe I should make this a little clearer by saying that this is E of X over KT. And my goodness, somehow I've got the New York Times instead of my, well, I think I'll just make this bigger than, Well, that's apparently as big as it gets. Anyway, so this is why the Metropolis step works. And as I said, measurements, after you have a sequence of configurations distributed according to one's desired probability distribution, one measures any quantity depending upon them, such as the shape of the protein, by forming simply an average of the quantity over the various configurations xk. If the measurements are computer intensive, and they often are, then one allows several sweeps through the lattice between successive measurements. Now, one application of this was an important application in particle physics was invented by Wilson, by the way, who once was one of Glauber's students, not a thesis student, I don't think, but he was a student in one or more courses that Glauber taught at Harvard. He was also the son of a Harvard professor. In any event, to simulate what lattice gauge theory on a lattice, Wilson represented space-time as a lattice of points in d equals 4 dimensions. And he separated two nearest neighbor points by something called the lattice spacing A and joined them by a link. He put, sorry, that's a gauge group element U of SU3 on each link. Sorry, I guess I should have read this yet again. For each elementary square of the lattice, the plaquette variable U sub P is the product of the elements of the gauge group around the square. So it's U1, U1, 2, U2, 3, U3, 4, U4, 1. The Euclidean action of the theory then is the sum over all the plaquettes of the lattice of these traces. Beta here is 6 over g squared, is inversely proportional to the square of the coupling constant. So the coupling constant squared is kind of playing the role of temperature. He approximated the path integral of the continuum theory then by an integral over SU3 on each of the links. The problem was that even on a space-time lattice consisting only of 20 points in each of the 4 directions of space-time, so in other words, you take our infinite universe and collapse it to something that's 20 by 20 by 20 by 20, still, Wilson's lattice gauge theory is an integral over 5,120,000 variables. So it was just dead in the water until Michael Kreutz applied Monte Carlo simulations. Kreutz published his computer program in PhysRevD, and the field of lattice gauge theory took off. By the way, Kreutz has a user-friendly website, latticeguy.net/lattice.html, where you can find various programs and play with them. I think they're all written in C, and they're quite cute, nice programs. One of them is probably the simplest of all the programs is something called puregauge.cc on a 6 to the 4th lattice. So this isn't 20 to the 4th, this is 6 to the 4th. And you can run it from low temperature, beta equal to 1, to high temperature, beta equal to 0, and back again, and you can exhibit the hysteresis of a first order phase transition by measuring the action as you go from low to high to low temperature again. You get this hysteresis loop, which is an indication of a first order phase transition. This program is particularly simple because it's just a very simple group, Z2, which has elements 1 and -1. Highly multiple integration. Well, suppose you have this is again back to integration, but it's a slightly different point of view. It's the use of the Metropolis step to integrate. And so suppose you have a function of many variables, and suppose you can find a positive function g of x that's similar to f, and you know the integral of g. So then you define a probability distribution g of x divided by the integral of g, and then you find the average value of I of g f of x over g of x. So in other words, this is equal to that. This g of x over I of x you call your probability distribution. And so then you do the Metropolis step not with the Boltzmann distribution, but with this p of x. And you then measure the ratio f over g. In quantum field theories, the partition function e to the minus beta or h, beta being 1 over kt, is a path integral. And it's in simple quantum field theories, it takes this form. And in the simple case, h is just quadratic in pi. And so this is a Gaussian integral over pi. So you can do the Gaussian integral over pi with your fingers, and you wind up with an integral just over phi. And the integrand then is an exponential of something called the Euclidean action L sub e. And the Metropolis method then works very well for theories like this. On the other hand, there are some theories that are awkward, and these awkward theories are ones in which the formulas for the momentum or the momenta in terms of the fields and their time derivatives are complicated and too complicated to be done analytically. So let me put in a 2 there. Are too complicated to be done analytically. And David Amdahl, who got his PhD last year or the year before, suggested integrating numerically over the momenta for such theories. And is explained in his PhD thesis. He and I have done this for a variety of awkward theories and also for some very awkward theories in which no algebraic formulas exist for the momenta. So you can't get anything like this expression here. This Monte Carlo method is really so robust and of such broad applicability that you can use it to solve arbitrary problems as long as you can generate a suitably big space of random plausible solutions, and then as long as you can test each solution to see how good it is at solving the problem. So once again, it's a matter of randomness plus selectivity, and you need to formulate the criterion of selection mathematically in the computer program. And so what you do is if you have your quality function Q of S, which is the criterion of when a solution is better or worse, you just use the Metropolis step with based on this quality of the solution. And so once you have Q of S formulated, you just generate zillions of random solutions and select the one that maximizes Q over the whole space. And you use P of S as Q of S. You just set P of S equal to Q of S. And it turns out, of course, that nature was way ahead of us by a few billion years, or in fact, perhaps in other parts of the universe, several billion years, or if one takes a modern view of inflation, then for all time, thought of as infinite in this case, evolution has been solving this, applying the Monte Carlo method. Well, anyway, I'm going off on a tangent there. So nature has applied the Monte Carlo method to the problem of survival. As a measure of the quality of a given solution, nature used the time derivative of the logarithm of the population. The space of solutions is the set of possible genomes, leaving aside DNA methylation, histone acetylation, other epigenetic changes. We can idealize each solution or genome as a sequence of nucleotides by some thousands or billions of bases long, each base B being adenine, cytosine, guanine, or thymine. Since there are 4 choices for each base, the set of solutions is huge. For humans, the genome has 3 billion base pairs, and so the solution space is a set with 4 raised to the power 3 billion, or 10 to the 1.8 billion. Raised to the power 1.8 billion. This space of solutions is obviously just absurdly big, because a Google, after all, is only 10 to the 100. This is 10 to almost 2, the raised to the power almost 2 billion. So that's why evolution works. That's why some dirty water billions of years ago was able to turn into Edward Witten, who gave us the colloquium last Friday. That's what I call progress. Well, this is actually the end of the talk, so I've ended early. I suppose that people conceivably might have questions, and I'd be happy to try to answer questions or create correct typos in this thing. I noticed a couple that I didn't get around to correcting as I went through this. So are there any questions or suggestions?
I have a question.
Yeah.
Can you hear me?
Yeah.
Okay, great. Well, thank you for the great introduction to Monte Carlo methods and some applications. My question is sort of naive, but when you introduce the idea of g of x as a proxy function for f of x,
I'm sorry,
I guess
could you say that once more? I didn't understand a certain noun that you used or adjective.
Oh, I said we were talking about doing an integration using Monte Carlo of a function f of x over an n-dimensional interval.
Right.
And then I believe you introduced a proxy function g of x. I don't know if that's the right way to show,
right,
the right way to describe it.
Right.
And so I was just wondering what's a good way to come up with the function g of x? I mean, I guess this is like importance sampling, but how do you estimate g of x?
No. Well, you're absolutely right. You put your finger on the weakness of this particular method. Because there are 2 aspects of g of x that you need. It needs to be similar to f, and you need to know what its integral is. So it needs to be easily integrated analytically or numerically. And then it has to be suitably similar so that the method works. Now, this is actually an equation here. So even if it's not, the optimum function g of x, this should still give you a reasonable answer when you do the Monte Carlo here. But of course, the more similar g is to f, the better this approximation will be. And of course, you need to integrate g numerically or analytically. But I don't have any, obviously there's no rule of thumb for getting them because, or at least I don't know of any, because
Do you have any example?
Because obviously every function f would be a different g. One thing that does occur to me now that you pushed me to this with this question is you could take your n-dimensional space, put a lattice on it, compute f at each of those points, call that g, and then say that g is just constant over each of the cubes, each elementary cube, and it has the value f had at a particular point there. That's kind of a Lebesgue approach to the approximation. So I suppose that'd work. Let me tell you one thing that I don't like about lattice gauge theory, and it's that you see the continuum path integral is actually an integral over gauge fields, not over group elements. And the gauge fields are supposed to be integrated from minus infinity to plus infinity. Wilson instead says, we're going to integrate over group elements. This is a compact group. So in the case of SU2, it's a sphere in 4 dimensions, the surface of a sphere in 4 dimensions. In the case of SU3, it's something like that, but in, I guess, 8 or 9 dimensions. So this is called compactification, and there are errors introduced by this Wilsonian compactification. On the other hand, the people who have devoted their lives to lattice gauge theory say that, well, their computers are fast enough and strong enough so that this doesn't matter because they use a lattice spacing that's small enough so this doesn't matter. And they're probably right. I spent most of my time working on lattice gauge theory, trying to actually integrate over the gauge fields. Someone who used to be here, Gary Hurlin, wrote some papers with me on this subject. Ooh. So let's see, do you or does anybody else have any questions? Because I could try to answer them. The basic,
I have another question.
yeah.
Go on. Yeah. That has to do with how is a quasi-random number different from a pseudo-random number? I mean, I understand pseudo-random number uses a particular sequence.
The difference is that the pseudo-random numbers are really random. Well, they're not really random, but they try to be really random. And part of and with randomness, you could have, in other words, suppose I moved this cursor around the screen, I'm doing it kind of randomly, but I probably am covering parts of the screen more than other parts. With quasi-random numbers, you ensure that your coverage of the interval 0 to 1 is uniform. It's not only random, but uniform. And I remember once, as I was looking for my seat at a Harvard colloquium that I was listening to. I was talking to somebody and mentioned that I had gotten from Los Alamos a cute program for doing this kind of quasi-random numbers. And who was that marvelous man who invented 21 centimeter radio astronomy and so many other things? Anyway, he was sitting there and he said, that method is better. And I turned and looked at him, and I stupidly didn't take his advice, because I didn't know that he knew so much about everything. Anyway, oh, I'm terrible with names, and I've now forgotten his name. He's one of the Nobel laureates. He unfortunately died maybe 10 or 20 years ago, maybe 30 years ago. He did research not only in radio astronomy, but in molecular beam physics, nuclear magnetic resonance, just all sorts of things. I remember a story I was told about him, and it's that a medical student came to see him one day and said, this medical student was bored with medicine, and he said, can I do some research with you? And this person, whose name I forget, said no. And the student said, why? And the person, who of course was a Nobel laureate, and as I said, knew almost everything compared to most people, he said, well, because I don't know what to work on. And so he in other words, didn't want to take on the student because he didn't think he knew what to work on. Eventually, the student insisted, and they did some very good work on how bacteria can swim in solutions. So let's see.
Would that be Nico Blumbergen?
No, it was not he. This guy was, well, I mean, all right, to find his name, to find out anything, you Google it. Where the hell is Google on this screen here? Oh, it's over here. Oh no, that's the damned New York Times. All right, let me just go here. Where is? Okay, 21 centimeter astronomy. Well, let me just say, I can't find it here. Well, this is a lousy web page if they don't mention this man's name, because he invented the whole field. And by the way, his request for funding for this was, he asked for $500 to construct a radio telescope. Then, yes, Purcell, thank you. So one of the students gave me the Edward Mills Purcell, yes. And that's who it was. He was a lovely man and an absolutely brilliant physicist. And the existence of MRIs is something that is a consequence of his research in magnetic resonance. He was just remarkable, and he was an extraordinary teacher of undergraduate quantum mechanics at Harvard. I wasn't an undergraduate there, so I didn't take his course, but it would have been lovely to do that. Anyhow, well, we are kind of out of time. Is there another question that would get me back on the mathematics of the subject rather than silly reminiscences? Well, anyway, I guess I should somehow distribute the typo free, or let us say typo corrected, first or second attempts at correcting this the slides. I'll certainly send them to Professor Duan, who can make them available to anyone else, or if anybody sends me an email, I'll send you back the slides. I think I'll also put them on the class webpage for 466, which is the course I'm teaching now in mathematical physics. By the way, this is drawn from chapter 16 of the second edition of my book on, the book is called Physical Mathematics. And it's also drawn to some extent from the chapter on path integrals. David Amdahl and I, well, also from David's thesis. Okay, well, I'm going to stop now if there are no further questions. And
Thank you, Kevin.
You're welcome. Thanks for inviting me and giving me the opportunity to talk. Have a nice weekend. By the way, there's a nice colloquium coming up at 3:30 that's of political and moral interest. I assume I agree with the politics, but I'm not sure because I haven't heard the guy talk. All right, I'm going to end it now. Bye.